All right, so now we're going to do a quick Gauss's little example problem. And here we're given a sphere, and the sphere is made up of, first in red, this is an insulator, and it has a charge density of rho. And this is a conductor, and it has a charge density of sigma. So just real quick, remember that rho is basically charge per volume, which would have units of coulombs per meters cubed. And then sigma is charge per area, which would have units of coulombs per meters squared. So now what are we looking at? We're looking for the electric field on the intervals given. So 0 to R1. R is simply the radius of the Gaussian sphere. So when the Gaussian sphere has a radius between 0 and R1, that's A, between R1 and R2, blah, blah, blah. So what does this look like? We're looking at this. In red, we have our insulator. And from 0 to this first radius, it is empty space. This is like the cross section, basically. And then from this R1 to R2, we're inside our insulator. And then from this R3 to R4, we again have empty space. And then over here is, what is that? R1, R2. Okay, that's supposed to be R3. Okay. So then our R3 to R4, we are inside the conductor. So, oops. How do we do this? We can just use Gauss's law from before. So surface integral of E dot of dA is going to equal Q and C over epsilon naught. Now remember, we're using a sphere, so we just say 4 pi r squared. Magnitude of electric field times the surface area of a sphere, 4 pi r squared, equals Q, E, and C over epsilon naught. So now electric field equals Q, E, and C over 4 pi r squared epsilon naught. Nice. We're going to use this formula for the entire problem. So now, let's say, okay, part A, 0 to R1. What is 0 to R1? That is empty space. So if we are in empty space, we are not, there's no charge in empty space. There's nothing there. So our Q, E, and C is just 0. Q, E, and C is in the numerator. Therefore, our electric field equals 0. Empty space. Easy. All right, part B. R1 to R2. So now we do have some charge because we have this volumetric charge density, rho. So now we just say, follow the formula. It's the same formula every single time. Q, E, and C over 4 pi r squared epsilon naught. Now what is our Q, E, and C in this case? It's the charge density times how much volume are enclosed. If we have rho times volume, if we multiply this volume to the other side, we're just left with Q. That Q is going to be our charge enclosed. So we just say it equals rho times, what's the volume of this little section? So the volume of a sphere is 4/3 pi r cubed. So now we have this section of a sphere. So we're saying, okay, we're gonna take the outer sphere minus this inner sphere. The inner sphere radius is R1. The outer sphere radius is a little bit trickier. So we're saying we're going between R1 and R2. So the instantaneous radius, the radius at any instant of the Gaussian sphere, will be our outer sphere. So we can't just call it R2 because we have to account for every possible radius of the Gaussian sphere. So our outer radius is just going to be little r, and our inner radius is defined to be R1. That gives us this row 4/3 pi little r cubed is outer minus the inner sphere 4 pi r1 cubed. Okay. That is just the Q answer. Now you just plug it in. So you say E equals, just factor out 4/3 pi, and you get this. Still divided by 4 pi r squared epsilon naught. Now, electric field is a vector. So we need to add, we can take away the magnitude and add a unit vector r hat. But first, we gotta cancel this stuff. So 4's cancel, pi's cancel. We're just left with rho little r cubed minus r1 cubed divided by 3 little r squared epsilon naught. Then we can just slap an r hat at the end and it will all be good. So that takes care of part B. Now, what is part C? Part C is from R2 to R3. Now again, what are we in? This area right here is all empty space, right? So when our cylinder, or my bad, when the sphere has a radius between R2 and R3, it's not enclosing any more charge. However, it's still enclosing this charge in the row from earlier. So we have to account for that. So we can just, it's going to be the same formula. So you can just say, find the QE and C is really, that's what it's asking for. The QE and C here is still going to be rho times the volume. Now, we're outside of this R2. We're past it, which means no matter how far past this R2 the Gaussian sphere is, it's always going to be enclosing the same charge, which includes the charge from R2 minus R1. So now, instead of having this little r as the outer, we can just say R2 as the outer. So we'll say, okay, 4/3 pi r cubed, oops, pi r2 cubed minus 4/3 pi r1 cubed. That's going to be our QE and C. If we plug that into our formula, 4 pi r squared, we're just going to get, again, factor r2 cubed minus r1 cubed divided by 4 pi r squared. Now, final answer, take away the magnitude, cancel out pi, cancel out the 4, rho r2 cubed minus r1 cubed divided by 3 r squared. There's supposed to be epsilon naughts here. Cannot forget those. And can't forget your unit vector. Okay, that's good. Looks good to me. Now, what's part D? Part D is R3 to R4. So where is that? That is from here to here. Now this blue thing is a conductor. Conductor with a charge density, sigma. But remember, conductors are weird and they hate electric field. So if your interval is inside a conductor, it will always be 0. Because conductor. And you can probably look up why, but for all this, you just need to know if it's inside a conductor, it's 0. Now, E is when, I should write it down, R is greater than R4. Now, if we look at this sphere, or this one, same thing. When R is bigger than R4, we would now be enclosing our entire thing with the Gaussian sphere. So you can just say, what is the charge enclosed? Q, E, and C equals, now we're still enclosing the previous charge from the last one over here. So we can just copy down that charge enclosed first. So rho times 4/3 pi R2 cubed minus 4/3 pi R1 cubed. That part stays the same. But now we're adding charge from this conductor. It has charge density sigma. And basically that means there's a sigma charge density, as in a charge per meter square that only exists on the surface. And the reason it's only on the surface is also because it's a conductor. It's only going to have the charge on the surface. So now we just need to know how to get charge out of sigma. Now before, we said that with rho v equals Q. Now with sigma times A is going to equal Q. So we just need to multiply the charge density times the area on which the charge density exists. So we know the charge density is on the outside of the outermost shell of the sphere. So we can just say sigma times area. Now the area that this sits on is the area, surface area of a sphere at the radius. It's at a radius of R4, so we can say sigma times 4 pi R4 squared. Now we can plug that into our formula. Q and C over 4 pi R squared epsilon. Again with the rows. R2 cubed R1 cubed plus 4 pi sigma R4 squared all over 4 pi R squared epsilon naught. Then we just gotta simplify it. So there's a pi in all of these, there's a 4 in all of these, and then we can take away our magnitude, rho R2 cubed minus R1 cubed plus sigma R4 squared all over R squared epsilon naught times R hat. And I forgot this row over, row thirds. Okay, That looks pretty good and looks like a good answer. So that's pretty much it for the sphere. And it's very similar if you do a cylinder. All you do is you use the cylinder formula instead of a sphere. So I'll do that one in the next video.